So good Monday afternoon, everyone. Welcome to lecture 18, Maths for Construction. So today's 27th of June, right? Last week, we did some statistics, standard deviation, how to calculate it. We started with probability. We had some definitions. We worked some examples. And we're continuing with the examples in the book to help us understand this idea behind probability. Right? So what we want to talk about is dependent events, right? So just before that, briefly, expectation is it's a number. It's a measure of how many times you expect something to happen out of a certain set. Okay, so the example is if you're coming to late, on average, your probability of coming late to work is 0.5. Then half the time you're late, half the time you're early. So in a week of 7 days, your expected number of days you're going to come late is half of 7, which is 3.5, right? So that's the idea of expectation. It's a number, right? It tells you on average, it's like the mean, on average, how much times an event would occur in a certain set of trials and a certain number of experiments, right? Similarly, if you're throwing a die, a single die, what could be a score? It's 1 or 6 scores, right? So if you throw a die, say 10 times, what is your expected score? Right? Now, sometimes you might get 1, then 2, then 3, then 4, stuff like that, right? So your expected score is kind of like the halfway mark in a sense, right? But that's kind of different. Calculating that is kind of different, and we'd see, that really yields a distribution, probability distribution. And what a probability distribution is, it tells you the probability of a certain variable having a certain value. Okay, so when we want to get to more meaningful work, we examine variables that can have values, and the probability of it having a different value is different. Okay, so think about the score on a die. It could be 1, 2, 3, 4, 5, or 6, right? So you have your scores, and what is the probability that you get a certain score? Each of the scores is 1/6, right? So that's a probability distribution there. For each score, we have a probability of getting that score, right? The variable being, we could call it X. X is the score on the die. That has a value, and associated with that value is a probability we could get that value. So that's what we're heading towards. So what is dependent events? Dependent events, essentially they depend on each other, right? If you have a bag of red and black balls and you draw one ball and you keep it, then it affects the other ball you're going to draw, the second ball. It affects it because now you have less balls in the bag, and you potentially could have less red balls if you drew a red ball first. Or you have less black balls if you drew a black ball first. So the first draw affects the second draw, right? That's the idea with dependent events. Some events depend on each other. Independent events, they don't affect each other. That's kind of like what they're saying here, right? If you're replacing the balls in a bag, then one draw wouldn't affect the other one because the bag has the same composition of balls each time, each trial, right? We have conditional probability, a concern with the probability of one event happening given that another event happened, right? So like, again, the example with the ball, What is the chance that your second draw you get a red ball, given that the first time you got a red ball, right? It's questions like that. You know, for dependent events, we have conditional probability because the probability of one event depends on what happened in the next event, right? So we have the addition law for probability. This is for mutually exclusive events. Essentially, the events cannot happen at the same time, right? So it's like throwing a die and getting a 4 and getting a 6 at the same time. Those events are mutually exclusive. You can't have the same two things happening at the same time, right? Sorry, two different things happening at the same time. When events are mutually exclusive, then or meaning either one happen or the next one happen. Obviously, you exclude the both, right? The both of them can't happen because again, they're mutually exclusive, right? So when we want to know or, we add probabilities together. When we want to know and, meaning the two events occur at the same time, which is not always possible, right? Depends on the problem. The and for joining probabilities mean that you multiply the probabilities together, right? So look at some work examples here. We went through this here. We had 20 men and 33 women. What's the chance of getting a man? What's the chance of getting a woman? A simple division for these here, right? They say find the expectation here of obtaining a 4 upwards with 3 throws of a fair dice. So expectation is average occurrence, and the probability times the number of attempts. Okay, so the probability of obtaining a 4 is 1/6, and if you make 3 attempts, right, it's 3 by 1/6, which is a half. It's really that simple. You multiply the number of events by the probability of an event happening. So you have a horse race here, 10 horses running, first and second. Again, we kind of went through this before. This shows you mutually exclusive events and a simple division, right, of the probabilities. This question here talks about failure due to temperature, vibration, or humidity. We have different probabilities for devices failing. And they want to find the probability. I'm not sure what this one is, fails due to excessive. I don't know if it's temperature, vibration, or humidity for that question here. Fails due to excessive vibration or excessive humidity, right? That's vibration or humidity. They can't fail at, for those two events at the same time, so they're mutually exclusive. So you add them. The and is you multiply them, right? I'll give you all some questions, so we'll try some questions here where we have some answers. So they say a batch of 100 capacitors, 73 that are within, 17 below, and remainder above. So you have normal ones, you have ones that are too high and ones that are too low. So they're asking if you randomly select a capacitor and then a second capacitor, what is the chances that both are within the required tolerance values with replacement and without placement? Okay, so the first selecting a good capacitor is 73/100. If you replace it, the second one is the same thing, 73/100. So we are, we get these two things at the same time. So that's and. So I multiply the probabilities here. The probability I get the first one is 73/100. Then the probability I get the second one is again 73/100. I multiply them, right? So these two events occurring at the same time. Below is 17. And if you didn't replace, now you have 99 capacitors. So above required threshold, we have 10 above, that is the remainder there. And now you have 99 capacitors. So it's still multiplying, but you're multiplying 10 over 99, not over 100, because the bag of capacitors is missing a capacitor now. It's not 100. So things like this, about with replacement, without replacement, and so on. We try problems like that here before we could go on, right? We did this question last week. You throw 2 die. What's the probability that your total score is 8, right? We saw how to do this last time. We draw a diagram. Well, we didn't draw a diagram. We list out the possibilities here, right? 5 possibilities out of 36. So that's why it's 5 over 36. You can try to do some questions here and then do further work on probability with replacement and without replacement, right? So let's try number 5, right? Let's try and do that. Even though we have the answers here, try and say how you would get these. If you could get these answers here, what would be the mathematics you would write to get these answers? And I could give you a custom question just now. Now, these types of questions where you see and or and not, right? They give you these rules here for and, multiplying, or adding, but I find as a little too simplistic and people really don't understand what is happening here. So the idea is we're doing number 5, we're trying to get these answers here. We want to reason our way out. But I might have to cover some diagrams about probability with 2 events. So here, I talk about 2 events. It's best to look at these things as Venn diagrams from set theory, right? So we have 2 events, A and B. Think about what it means when one happens, okay? The A, the circle on the left A shows you event A happening, right? And there's a small portion, this yellow portion in the middle, where A happens and B happens at the same time. The red portion is A happening, but B doesn't happen. Of course, for B to happen, it have to be in the circle, the second circle on the right, the B circle, right? So you see, generally, if you have 2 events, yeah, and several things could happen. None of the events could happen. And that's the blue shaded area in the diagram, right? The blue shaded area is where none happens, neither A nor B happens, right? Then you could have A happening, but B doesn't happen. That's the red. And you could have B happening, but A doesn't happen. That's the orange. You could have both A and B happen at the same time. That's the yellow, right? So we want to use set theory. The idea is an intersection and union to figure out what these things mean. So if you have 2 events here and ask the question A or B really means everything inside the circles, okay? So that really means A occurs or B occurs or both of them occur. Okay, that's what A or B means. There's a possibility that both of them can occur at the same time. If they can't, then they're mutually exclusive, and it means these circles don't intersect, which we will see in a while, right? But generally, for 2 events, if you don't know if they're mutually exclusive, then they could intersect. And if they could intersect, you have to be careful. Here, the idea of and, right? A and B. So that's really A occurs and B occurs together. together at the same time, right? That's the intersection, right? That's really the intersection there that they talk about. So we write here the intersection. And generally there's P away. By P of B, right? You multiply the probabilities for and because they're happening at the same time. And that's what the textbook is saying here for and when things happen at the same time and join any probabilities we multiply. Okay. So for if somebody asks you, and was it probability that A occurs and B occurs? Generally you multiply them, but if they can't occur at the same time, then that probability is 0. That's like, for example, you have two events. You roll a die. One event is you get a 2, and the other event is you get a 4. Those two events cannot happen at the same time with one roll of a die. They are mutually exclusive. So if A is getting a 2 and B is getting a 4, probability of A and B happening is 0. You can't really multiply them like that because it's not possible for them to. You don't multiply 16 by 16 to get 1 over 36. You can't get a 2 and a 4 at the same time on one row. Now you can get a 2 on the first chance followed by a 4 on a second row. You'll multiply those two probabilities together, right? 16 by 16, right? But not at the same time. Those are different experiments. I'm talking about in one experiment, right? So you see a probability gets tricky. Sometimes we're not sure if they're talking about two experiments or one experiment. What we're talking about is one experiment here, where we have several outcomes. Is it possible for these two outcomes to occur at the same time, right? And the answer is generally yes, it's possible for these two events to occur. That's the yellow thing you see there, the intersection, right? So this question here, number 5, where let's see this here. Let's see if I could probably copy this and paste it here. This would be our question 1. Section 1. Let me try and paste this. This is how to fix this. B happening is 2/3, A happening is 3/5. So what do they want? Right. So they say chances of A happening is 3/5. So it's possible that A will not happen. Yeah. 2/5 is that possibility that A doesn't happen. Similarly, chances B happening is 2/3. Again, because this is not absolutely one, then it's possible that B wouldn't happen. So it's possible that both A and B will not happen. That's the blue area, the blue region here, where both A and B didn't happen. I mean, so this first probability here, both A and B happening. This is the intersection. This is the yellow stuff here. So it means you have to multiply the probabilities. Generally, you have to multiply them. So probability A and B. Actually, I could just steal this here. We multiply the probabilities. So this is so 3/5 multiplied by 2/3. The 3 will cancel to give 2/5. Right? So this is the probability that A and B happens, which is the intersection. Okay. Part 2, they say only A happening. Now, for A to happen alone, that means you have to take away you have to subtract the intersection from the whole of A. So what we could do, we could subtract this 2/5 from the 3/5, right? That will get 1/5. So let me duplicate this. This here could be A only, right? How many ways to do this? This is probability of A minus the intersection. So this is 3/5 minus 2/5, which is 1/5. Right? That's A only. Because you see, the entire of P of A, right? The possibility that A happens inside of it has the possibility that B happens as well. Yeah. Both A and B can happen at the same time. So the chances that A happening alone, which means B does not happen, one way of doing it is just subtracting the intersection from the full thing, right? Another way for A only is that A happens and B does not happen. So we could write that as probability A and not B. And that's the same thing. Huh? What does A intersect with not B? A is the entire left circle and not B is everything outside of B. So A and not B is the red part, right? Now, this is an and. A and not B means A happens and B does not happen. So we could represent that as multiplication of events. We could say that, okay, A happens and B doesn't happen at the same time, because it's possible. It's possible for A to happen and B not to happen. So probability that A happens is 3/5. So you're multiplying 3/5. And the probability that B does not happen is 1 minus the probability that B happens. So I could write this here. One minus right? Probability that B does not happen is 1 minus the probability that B happens. Either B happens or it doesn't happen. Okay. This is 3/5 times 1 minus 2/3. So this will be 3/5 times 3/5 times 1/3. Threes cancel to give 1/5. So this is our next way of doing it. We get any same answer. You can multiply probabilities because these are two events that could happen at the same time. Or you could just use your notion of the Venn diagram. If A happens, it means the whole of A has to get subtracted the fact that B and A happen. So subtract the intersection from it. So it's two ways to arrive at the answer 1/5. Okay, based on the diagram there. And they have a similar thing here. Look, only event B happening, right? Here's a similar argument to these two here, right? And look, this one here, either A or B, or A and B happening. That's the whole thing. That's this whole two circles joined together. But that's what this is. That's what they call a union. The union is either A happens or B happens, but you have to subtract the intersection because the intersection is contained in A and B as well. So if you add A and if you just say pair A plus pair B, you will add the intersection twice. So you need to subtract it to add the intersection once, right? So for part, use this idea here to do this third part and then find out what the union is using this formula here. That's the last part is they're asking you the union, right? I'll fix this up a little bit. Okay. So finish it out using this kind of similar work in here if you didn't get it for 3 and for 4. So only when B happening is very similar to part 2, only when A happening. We have two ways we could do it. We could look at it as for B alone to happen. If you watch the diagram here, that's the orange part. It means the entire of B, we need to subtract the yellow from the whole circle. The entire B circle is probability of B, which is 2/3. And we need to subtract the yellow part, which is the intersection, which is 1/5, right? So we could do that here. We could say probability of B only is the probability that B happens, which is the entire circle, minus the intersection. Probability of B is 2/3. So let's see, 2/3, right? Minus the intersection. What is the intersection? The intersection we found in the beginning, the first part, we found out to be 2/5, right? So 2/3 minus 2/5. And you know, you work with equivalent fractions there, right? So you express each of these guys as something over 15. Right? So 2/3, we need to multiply above and below by 5. 5 3s are 15, 5 2s are 10. And then this one, we need to multiply above and below by 3. So 3 by 5 is a 15, 3 2s are 6. So now we have the same denominator, we could just subtract numerators, right? 1 10 minus 6 is easy enough to do. That's 4 over 15. So as the chances of B happening alone, only B happening, is 4 over 50. There's another way to do this here. Same way we did the A only, right? Probability of B only is the probability of B happening, sorry, and A not happening. That's here. B happens and A has to not happen, right? So that's B by A complement. Because, you know, intersection means two events happening at the same time, which is possible. The AND rule says to multiply them, okay? So when we have an intersection, we multiply probabilities. That's the product rule, as you see up here. Let me go back, laws of probability, right? The product. So that's AND. When both events happen, you multiply them. So here, B has to happen and that's what the intersection is, and A has to not happen, right? Because they say B only. So A cannot happen. So for sure, A complement has to happen. Multiplying these things, this is PB by 1 minus PA. PB is 2/3 and PA is 3/5. So that's 2/3 by 2/5. That's 4 over 15. So you see we get it 4 over 15 in two different ways, right? Both ways are correct and they need to make sense to you, right? What about part 4? What is part 4 asking for? Either A or B or A and B happens. So that's the total, the union. That's the union. Because A could happen, B could happen, or the both of them in the middle could happen. So that's really the union here. So, you know, we steal this and we put it here. So what is this? What's the chances that A happens the whole of A? As 3/5, I believe. Steal a frock. So PA, which is 3/5, plus PB, which is 2/3, minus the intersection. And the intersection is 2/5, which we found up here. Right, so I could say 3/5 minus 2/5 is 1/5. One-fifth plus the 2/3. If we represent them as something over 15, one-fifth multiply above and below by 3, and the 2/3 multiply above and below by 5. So you get 12 over 15. See here, this is the total probability. They say either A or B, or A and B happening. Right? So this feel like is the total probability they're asking for. I get 12 over 15. But the book says 13 over 15. Right? Maybe they didn't ask the question properly. Maybe they meant either A or B, which is the total thing, or the intersection. So I mean you had to add the intersection one more time, which is, remember, the intersection is the 2/5. Right? But if you add 2/5 to this, you will get more than one, which don't make sense, right? So I'm not sure how they get 13 over 15 there. So it probably means A alone or B alone, or A and B happening. But I mean, that's the same thing as the total. Unless they mean you add these three things here together. Right? That could be what they're asking you. If you see how they added here, they say either A, which is A alone, or B, which is B alone, or A and B happening. Those are three mutually exclusive things. What they're asking here is to add the red, the yellow, or the orange. Add three of them up. So that's 2/5 plus 1/5 plus 4/15. Unless they mean to do that. What if we do that? What if we say what if this is what they're asking for? A only plus B only plus the intersection. I think this is what they're asking to get that answer. Right? Which is you're adding the three things. A only is 1/5. B only is the 4/15. And the intersection is the 2/5. That's the 13 over 15 there. Right, so maybe they were trying to ask this and they didn't really do it properly. I think I made a mistake here. This is supposed to be 3 over 15, right? So it's 13. So it works out to be the same thing, right? So it's correct, right? The way they stated it here is very weird the way they stated it, but it don't matter if you do it both ways because you're adding up the pieces. Now, if you watch how they ask you to do the question, they made you find each of the 3 pieces separately, and all you have to do is add them up in the last part here. But using your knowledge of the Venn diagrams and what the probability means, you could just add A and B and just subtract the intersection. You see, the intersection is in A and it's in B. So if you add A and B, you will get an extra intersection. That's why you have to subtract it, right? So again, 2 ways of doing it, right? The reason why you could add up these here is because of a reason we're going to talk about now called mutual exclusion, which we saw in the book. They talk about, where was it? Did they mention it? I don't think they actually did. And that's what we want to talk about now. This last way of doing it. The reason why I could add these probabilities together is because they don't have anything in common. Generally, you can't just add 2 probabilities together to mean or. Like A or B is not just A probability A plus probability A. If they could occur at the same time, you have to subtract the intersection. So that's what we want to talk about now. So mutually exclusive events. If an event A can occur or B can occur, but not both of them at the same time, they're said to be mutually exclusive. They do not overlap. I mean, an event diagram doesn't look like above. It doesn't have a yellow part here. It's empty. So it's like the 2 circles are separate, right? It's referred to as the OR rule, right? Which is this rule here that they're talking about. The A or B. You say if they're mutually exclusive. So you can't just add 2 probabilities together just so to mean or. They ought to be mutually exclusive, right? So there's a disclaimer here. Sentence is a disclaimer sentence. The or now, A or B, becomes just add A or B. And this works when they're mutually exclusive, when they cannot occur at the same time. If events can occur at the same time, A or B, which is like this here, you have to subtract the intersection because there's a non-zero intersection. Event A and event B can occur at the same time. So this is how the diagram would look like. But if they cannot occur at the same time, it gets easier, just add the probabilities, right? So we'll try a question just now to see how this works. So look at this question 2 now. And this question would use all the stuff we did so far. General Venn diagram for 2 events, as well as a special one for mutually exclusive events. You have to look at the question and think and determine which situation you have. Do you have mutually exclusive events or not, right? So we have a single card drawn at random from an ordinary pack of 52 playing cards, right? 52 playing cards have 4 suits, Each suit has 13 cards, hearts, diamonds, clubs, and spades, right? They're asking for the probability that the card is a club or a diamond. And then what's the probability it is a club or a king? So you have to take your time and think about what these two events are. For this part, the two events, one, you can say C, P of C is a club, and P of D is a diamond, and P of K is a king. And you can find these different probabilities and see what it is you're dealing with based on the event diagram. It's not formulas. Try and understand that it's looking like formulas here, but this topic is not about formulas, it's about thinking. If you're thinking correctly, you will apply the wrong formula and get the wrong answer, right? Mathematics is not about formulas, it's about thinking. So you have to train your mind to think about these things, and that's what we're doing in class. The textbook, as I say, is not very great, but it's fairly okay. But to me, it doesn't really do a good job of explaining things properly. That's why I'm doing more notes here. And then, as usual, you have to do questions. When you do lots of questions of different levels of difficulty, you will understand the topic better. So try this question and tell me what your final answer would be. So what I'll do, I'll create some notation in the question, right? So let C be the event. Then put in quotes, a club is drawn. And we could, copy this. D be the event, a diamond. I'm showing you all how to answer this question. So king is drawn. Right, so now we define what C, D, and K is. Then we could use the notation P of K, P of C, that kind of thing. Right. So let's find these probabilities, right? What's the probability? Oops. What's P of C? What's the probability of getting a club? Remember, you draw one card from 52 cards at random, right? Let's say at random. So probability that you get a club. Well, how many cards you have in all? This obviously is a fraction. You have 52 cards. And how many cards are clubs? 13, right? So that is so you have 4 suits, right? So the chances you get one suit is a quarter, right? You could duplicate this. The same thing exists for D. What's the chance again a diamond? You have a quarter of the cards is diamonds, right? There's 4 suits, equal number of each one. So P of D is that. What about P of K? How many kings you have in all? This is the first thing I would do with a question like this if I'm not sure what I need to do, right? In a pack of 52 cards, we have 4 kings, right? So 4 over 52. We could reduce that, that's 1 on 13, but leave the fraction with the 52 in it because we might use that later on for something, right? So these are the chances here that things happen. And now I will start to do the parts. Now I could do the first part, right? These things, I need these things for all the parts. I need to know what these things are. For the first part, they say club or diamond. So they want, hold on. They want the probability C club or diamond. That's really what they want in the first part, a club or a diamond. Now think about it, right? If I tell you deal one card from a pack of 52 cards, right? And if the card you give me is a club or a diamond, I'll give you $10. Now, what's the odds of getting that? Just think about it. How many cards are clubs or diamonds? If you get a club, I'll get $10. If you get a diamond, I'll get $10. So you know you're adding up how many clubs and diamonds you have, which is 26, 13 of each. So this is really 26 over 52, which is a half. So you have the probability of getting a club or diamond is a half just by the numbers alone, right? That's one way of thinking about it. But how to use these numbers here to get that, right? The events C and D are mutually exclusive, since they cannot occur together, right? A card cannot be both a club and a diamond, right? So, you know, without just thinking of the numbers of cards in a deck, just using these values here, this is really P, C, is really that. And since it's mutually exclusive, you just add them. So a quarter plus a quarter, that's a half, right? That's how you do the first part. Again, you remember I said, thinking about it in terms of numbers, what is the possibility space when you say a club or a diamond? That's 26 cards. The possibility space is 26 out of 52. That's another way to do it, right? But if you had to do it based on these probabilities that we found here, without thinking too much, just understand that C and D are mutually exclusive, so you just add these two probabilities together. That's the lazy kind of approach where you know what the events mean, right? But you don't want to think too much. But without using these three values here, I could do this question, right? As I explained before, a club or a diamond, that's 26 cards, 13 of each, okay? So alternatively, So this part you could have solved with considering the possibility space of actual cards, right? We have 52 cards in our deck, but how many actual clubs and diamonds we have? You gotta add them up. You don't multiply them. You don't multiply by 13 to get 169. That don't make sense, right? If I tell you I'm gonna give you money if you draw a card and it's a club or diamond, consider your chances. Consider how many ways you could win that money. If you draw a club, you win. If you draw a diamond, you win. That means you have 26 chances to win out of the 52. That's roughly a half. Okay. Okay, so that's another reasoning behind. What about part 2? Okay, what are they asking for? A club or a king? Now, the set C is the set of all clubs and K is the set of all kings. Is it possible to get a king of clubs? That's an intersection of C and K. Event C and K can occur at the same time. They are not mutually exclusive. This is because we have a single king of clubs. Okay, that's the intersection. There is a card that's a king and a club, so they can occur at the same time. Now, without thinking about the actual cards, right? How could we find this? Right? Intersection is multiplication, right? So I could steal, where is it? This guy here. I just change the letters C and K. What if you didn't know that it was 1/52, right? C and K is a club and a king. We multiply club by king. Probabilities, you are multiplied, right? Probability of a club is 13/52. And the probability of king, how many kings you have in the deck? 4/52. When you multiply that out, right? You're gonna get 1/52. Because 13/52 is a quarter, and a quarter by the 4 will cancel to give 1/52. This is if you didn't know that you have a single king of clubs, right? If you didn't know that. This is the proof here if you want king and club. And what they're asking for is king or club, right? So they're asking for the union. So king or club, or club or king, right? Symmetric, is the union. And what's the formula for the union? We add them and we subtract the intersection. Right? So what's that? That is add two fractions and you subtract another one. What we adding? What is club is 13 clubs. A king, we have 4 of them. And we want to minus that one that is in the intersection. So you get 16 over 52. Now 4 is a, sorry. 4 is a factor of these two numbers, so it could reduce 4 into 16, 4, and 4 into 52, 13. So this is a probability that you get a king or a club, same as a club or a king, right? And you don't even need to do all this if you just think about the possibility space, right? If I tell you you're getting money for a king or a club, well, how many cards in the deck are kings or clubs? You have 13 clubs and you have 4 kings, but one of them is a king of clubs. So that's really 13 and 3, which is 16. By considering the possibility space, you could write down 13 clubs. One of them is a king already. So you just add the other 3 kings to that and you get 16. Those are your chances for king or club for winning that sum of money, that bet. If I tell you, you know, pick a single card, and if it's a king or if it's a club, I'm giving you money. Well, how much cards are kings or clubs? There's only 16 of them in the deck, right? But if you didn't want to think about a problem like that, you could use these formulas here and it would work. But just understand that the formulas are not a substitute to understand the mathematics, what's going on. That's why I'm giving you these problems here with cards. If you don't want to use the formulas, you could use the actual cards, and but you have to answer that question different. You have to say what are the cards, you have to list them out. 13 clubs, one of them is a king, plus 3 other kings. That's the possibility space for king or club out there 52. That's 16 on 52, that's 4 13s. So I hope this makes sense. So look at this word problem here. You go to the food court, sometimes buy food and drink, right? Not all the time. This kind of telling you, sometimes I mightn't buy anything at all, neither food nor drink. That's what it's trying to say. Sometimes I buy food and drink. So there are many different foods they eat. That talking about hot dogs, probability I buy hot dogs is 19 over 13. Right? As you see here, I kind of like hot dogs. That's more, it's a little more than half. Now the probability that I buy coffee to drink is 2/3. So there's a kind of high chance you're getting coffee as well. But it possible I may not buy coffee, and it possible I may not buy hot dog. It possible I might buy hot dogs alone and no coffee. Some days I might want to eat, I might just buy coffee alone and no hot dogs. Sometimes I buy none and just get pizza and a soft drink, right? So it have a lot of things happening here. So draw a diagram, think about what the different probabilities are. always start a question by saying what the events mean, because you're going to be using letters like F and G and R and M. Make sure and say what these things are, right, in the question. Don't just pelt us at a mathematics, P of F and P of M, and you didn't say what it is, right? That's not polite. You shouldn't have to figure out what your notation is. So they asked for three things. What's the probability you buy hot dogs and coffee together, right? You sit down and you buy hot dog and coffee. What about you buy coffee only for lunch? There's a chance, you know. It might happen that I might only buy coffee for lunch, right? Maybe I had a big breakfast, right? Or maybe I'm gonna eat something a little bit later, so I don't want to eat anything now. And what if I buy, you know, something else, right? That's not hot dogs or coffee. So you see neither, no, you know, none of them. That's that possible too. What are the different parts of the Venn diagram that these things correspond to? And figure out what they are, what these probabilities are. Okay, I'll give you a nice question. It's very obvious that you could get both coffee and hot dogs. But it's possible to get neither coffee nor hot dogs. Possible to get coffee alone. Possible to get hot dogs alone. Okay, there's a lot of things happening here. So draw a diagram, write out what your notation is, be pleasant about it, and do the mathematics, right? Hope you have fun with this one. So, you know, we start off with the usual statements that say, right? So we could say here, H be the event I buy hot dog. C be the event I buy coffee. Right? So I have H and C. So probability of H, they give us 19/30. Probability by coffee, that's C, 2/5. And they gave us probability or hot dogs or coffee. So HOC, right? It's 4/5. They gave us that. Now, you might think this is saying hot dogs and coffee. So, you know, for the first part, they want the intersection. Right? But you can't multiply H and C because that's only work for independent events. We go back to here. This formula is for independent events called the annual. See, they didn't really mention that here. They make you think you could always multiply A by B to get the intersection. That's not always the case. There's something called conditional probability, where the probability that something happens given the fact that something else happened is different from the fact that it's different from the probability that that thing actually happens. Like probability that A occurs depends on if B occurs. So P of A, given that B occurs, is different from P of A, right? The probability that A occurs. Whether or not B occurs, it affects the probability of A happening. Independent events, the probability of that A occurs, given that B occurs, is still the probability of A. Doesn't depend on B. Only then you could do these things here, like multiply. Right? As I said, this book not so great. You can't multiply H and C to get H and C because we were not told if these events were independent or not. And I mean, they might be dependent, right? Me buying coffee might be affected by my decision to buy hot dogs and vice versa. Me buying hot dogs might be, what might affect that is me buying coffee. You never know, the events could depend on each other in some way. If they didn't tell you and you look at the question and you're not sure, then you can't assume it. Any questions before, right? When we multiply events, these were independent, right? Right? Generally, you can't do it, right? So H and C, you can't just multiply H by C. Now, the fact that they give you a union here is very helpful because we have a formula linking the intersection with the union and the different events, right? So come here now, we could say the union is H C right? Now the union probability they give us as 4/5. So 4/5 is equal to 19/30 plus 2/5 minus the intersection. So you can change the subject at the intersection, right? So the intersection is this sum here minus that 4/5. So multiply above and below by 6. It's 7/30, right? That's the answer for the intersection. You basically use an event diagram. That's what these formulas are. Part 2, they're asking for you buy coffee only. So this, so let's say only. probability of C minus the intersection. Right? That's 2/5. That's 1/6. And neither hot dogs nor coffee is the outside. So that's just 1 minus the union, which is this. Right? Everything outside of H intersect with everything outside of C. That's just 1 minus the union. That's 1 minus 4/5. That's 1/5. Right? So you could find a lot of things based on this Venn diagram up here, right? Neither A occurs nor B occurs. That means it's the blue part. That's 1 minus the union, right? If A occurs only, that's all of A minus the intersection. That's what they did here. Right, so these should be the answers for this question. Hope it makes sense.